for this very first webinar on the Quantum in Practice series, which is organized by CCFR and TQCI. Let me just present briefly the CCFR. So it's part of the EuroCC project and serves as a French National Competence Center among 33 countries in Europe. Our objectives are to connect industrial, academia, and public administration with the right resources, projects, and training opportunities, and to map key players so everyone can access the most relevant expertise in HPC, AI, or quantum computing as today. So this center is led by TerraTech with 4 partners, Serfax, INRIA, Romeo and Client, and the participation of 21 mesocenters in France. Our missions revolve around the various actions that you see on the screen, with the constant goal of supporting you free of charge and in your different needs. So let me highlight just our company support, which is tailored to each need. Examples and interviews are available on our website and our YouTube channel. So to give you an overview of what we can offer and how we can help SMEs or other organizations in the use of HPC or AI. So let me now tell you a bit about our trainings. We organize 3 summer schools in HPC and quantum computing. And throughout the year, you also have access to many webinars and training on various topics and various levels. You can find the full list on our website. You can also connect to our LinkedIn so you don't miss anything. And all sessions are recorded, just like this one, so you can catch up anytime on our YouTube channel. This brings us to today, our new series. We are happy to launch today with you and that we organize with TQCI. It's Quantum in Practice. We are very excited to welcome you to this first session. Each webinar of the Quantum in Practice series will aim to explore technologies, tools, and real-world applications shaping today's quantum ecosystem. Each session will feature a quantum provider, and today we are very happy to welcome PASQAL with Vincent Martin and Christiane Beignot with us. So before starting, let me hand over to Emmanuel Vergniaud, which will present you TQCI.
Hello everyone. So TQCI is a TerraTech quantum computing initiative that has been launched in 2018 by some of our members who wanted to have a common reflection on quantum computing, organize skills development, and identify use cases. And we are part of the French network of Maisons du Quantique, quantum houses, and we help to consolidate the ecosystem by supporting collaborative projects. We organize seminars in partnership with industries to meet their expectation as closely as possible. And all the seminars are recorded. And as CCFR webinars, you can access this online using the QR code which is provided. And as Marie told us, we are very happy to launch this Quantum in Practice webinars to facilitate the transition to practice for everyone and in continuation of the seminars we have organized. And there is a lot of providers that are waiting for their turn, and I'm very happy to begin today with PASQAL. So I let the floor to Christiane and Vincent, and thank you very much for being there today.
Thank you, Emmanuel. I'm going to introduce myself first before giving the way to Christian. And after giving the first half of the session, I'm Vincent Martin. I'm a technical sales and technical account manager here at PASQAL for 1 year and a half now. I have a background in applied mathematics to quantum system and quantum physics I did my PhD at INRIA Paris and in the Quantic team, which spawned, by the way, Alice and Bob, another French quantum startup. And after that, I worked almost 2 years for ANSYS, the world-leading multi-physics simulation software company, as the first guy to see what quantum computing could bring to their portfolio of algorithms. Christian, if you want to introduce yourself.
Of course. Hello, everyone. Good afternoon. My name is Christian Begnot. I'm also technical business developer, technical account manager, and quantum solutions expert, much like my colleague Vincent. My background is more in computational fluid dynamics, so mathematical physics from the classical side, but I've been working with quantum computing for the past 5 years, and I've been with Pascal for almost 3 years now.
So, thank you, Christian. I'm going to begin the presentation. I'm going to share my screen.
Okay, just a quick reminder, if you have any question, please use the chat on the bottom right of the WebEx slide, and it will be answered by Vincent and Christian during the webinar.
Okay, so can you see my screen? Christian, can you confirm me that you are seeing it?
Yes, yes.
So first, what is the goal of this session? The goal is to really give you a hands-off approach to who we are at Pascal, what is our technology, and how to use our quantum processing unit or quantum computers, and to see that it is quite easy to use them compared to what you may think. The prerequisite for these sessions is basically only a working knowledge of Python, even if, of course, math and physics background will be helping tremendously to grasp like all the tiny details that we are going to talk about today. And of course, this session is recorded in order for you to have access to it later. The slides also, if I remember correctly, will be available. So don't hesitate to really focus on what we are saying and what we are trying to convey as information, and not to feel forced to read everything that is on the screen. And on the right, I give you a small preview of what Christian will show you in the second half of the session, which is what it looks like to use a real-life quantum computer. So my first half of the presentation will be in 3 chapters. First, a presentation of Pascal and its technology. The second, a presentation of what is quantum computing and quantum algorithms that could be solved on Pascal QPU. And then a small walkthrough of how do you design a very standard use case, a very standard sequence inside Pulsar. So first, let me talk you a bit about Pascal and its technology. So a small history, we were founded in 2019 in France by a group of physicists and engineers who have been working on the different technical bricks that compose our today's quantum computers for almost 20 years. To give you an example, our former CEO, Georges-Olivier Raymond, did his PhD at the end of the 90s on the technology of the optical tweezers, which is currently one of the fundamental blocks of how our quantum computers are working. In 2021, we did our first Series A of 25 million euros. In 2022, one of our co-founders, the Professor Alain Aspect, was awarded the Nobel Prize in Physics for all his works, and we're very, of course, proud to have among our founders such an important scientific figures. In 2023, we raised up to 100 million euros in Series B, with a notable fact, all the people from the Series A coming back to the Series B, showing great confidence in the capacity of Pascal to deliver a real and tangible products. And in 2024, we had several successes. First, technological successes, where we, for the first time, exceeded 1,000 atoms inside one of our quantum processors. Collaboration successes. IBM, which is one of the very important players of the quantum computing industry, has recognized us as one of the most advanced company in the industrialization of quantum computers. And so we made a collaboration with them, partly on how to integrate quantum processing units inside a HPC workflow. HPC for high performance computing. Maybe you know this anagram. I'm not used to talking a lot to public who are used to that kind of field with the HPC. And also, excuse me, commercial successes, as we were the first company in the world, and this is really something to note, to ever sell a quantum computer to a private, to someone from the private sector. And we sold it to Aramco in Saudi Arabia. Of PASQAL is to be a hardware provider, meaning that what we want to do in the end is to sell either quantum processing units on site or to sell cloud hours. And in order to reach this goal, we have already sold 5 quantum computers. 2 of them are already installed. So one in Bruyères-le-Châtel in France at the TGCC center, which was installed during the last year, and one in Jülich in Germany, another HPC center, which are all installed and ready to use. We are installing right now 1 quantum computer in Saudi Arabia in Aramco, and we will be installing a last one in Italy at the Cineca facility in the year 2026. And the 5th one is a quantum processing unit that we built in Canada, and that was sold to a consortium of private and public actors near Sherbrooke. What we are aware, though, is that quantum computing is not there yet. Like, it is still a nascent industry, and we need, as a future quantum hardware provider, to encourage the adoption of such a technology. And in order to do that, we helped different important industrial partners to develop use cases that use a quantum computer to its finest abilities, and to really try to reach as fast as possible a domain where using quantum is useful, meaning, like, it's the fable like quantum advantage. We prefer at PASQAL the term quantum utility, because this is when you will have an interest of using a quantum processing unit before a classical machine, and you would like maybe to use it for different reasons. Maybe you want something that gives the same result, but with way less energy that you have to put in your system. Maybe you want a slightly better solution. Maybe you want to have something a bit faster. So there is a lot of way to talk about quantum advantage, and this is where we prefer the term quantum utility, when there is something that the quantum computer brings you that would not be possible with the classical computer. And so we have done use cases with different companies. Of course, as we are a French company at the heart, we did a lot of our first proof of concept with French company. So with EDS, with Thales, with CACIB, and with CMA CGM. But we have also an international reach. Like, we have, for example, done proof of concept for BMW or for ANSYS. And of course, one of our biggest clients is Aramco in Saudi Arabia. So you probably, if you are in this class at least, you have probably already heard about quantum computers, and you might be a bit confused about, okay, I've heard about quantum computers, but usually maybe I've heard that it's kind of stuff where there are superconducting qubits. There are stuff that we need to freeze really, really cold near to the absolute zero. Or sometimes you may have heard about photonic quantum computers, and you're not exactly sure why there are so many technologies to build a quantum computer. And the reason is that there is not, for the moment, a definitive answers as to what is the best technology in order to build a quantum computer. For a classical computer, we have the answer. We know that the most efficient way to do it is basically, okay, you have semiconductors and various different pieces of technology, you power it with electricity, and this is by far the most efficient way to store and manipulate data on a classical level. We are not at this stage yet for quantum computing. Maybe you can try to represent yourself as the point in history where computers were very big machines. You had some vacuum tubes in order to, instead of transistors, and there was really some questions in how to realize physically the conceptual idea of a computer, meaning a machine that is storing and manipulating information. And we are at this era in quantum computing. So let me talk you briefly about the main technologies in this race. There is the neutral atom technology, which is the technology of Pascal. And the concept is that you are going to trap atoms with lasers, which are called optical tweezers, and you encode the qubits, so the information, in the atom's energy levels. So the most important company using this technology are Pascal in Europe and QEra and Atom Computing in the US. For the German people among us, there is also a new German startup who has been trying to leverage this technology, which is PlanQC in Munich, if I remember correctly. You have also the superconducting technology. Probably if you have already seen a picture with something labeled quantum computer, you have seen something which is a superconducting quantum computer. Like probably you have seen those big shiny towers of copper or something like a golden metal. It is a superconducting quantum computer. And in fact, it's not the computer that you see, it's the fridge to cool down to very low temperature the tiny quantum computer which is at the base of it. And so the goal of this technology is you have to cool down some electronic circuits to near absolute zero in order to leverage like the superconducting effects that happen at these low temperatures. And in fact, what you are creating is kind of artificial atoms with that technology. So this technology is quite old and it has been used by most of the big players in the quantum computing field, like IBM and Google Quantum AI. But the majority of the companies that are trying to build quantum computers were, until quite recently, majorly superconducting qubits technology. You have also the photonic technology, where it's very simple. You are using photons in light as qubits themselves. For this, so the very big player in the world is PsiQuantum, which has raised, I think, if I'm correct, like maybe $2 billion recently. So very huge investments. You have also the trapped ion technology, which is quite similar to the neutral atom technology, where you are confining and trapping ions or any basically charged atomic particles in free space with electromagnetic fields, a bit like the optical tweezers of neutral atoms. And for this, the two big players, maybe you have heard of them also, are IonQ and Quantinuum. And okay, I put quantum dots here. What you have to keep in mind is that there are maybe 10 others way to build qubits from the physical world we live in. And the stuff is that for the moment, of course, there are reasons to think this technology is a bit better on this point. This technology, maybe it's not going to scale well, etc., etc. But there is not a definitive answer as to which is the best technology in order to build a quantum computer. And we might even go up to a point where, similarly to operating system, we could have thought that in 50 years, there would be only one operating system left. And what we see is that there are 3 different operating systems. You have Linux, you have Windows, and you have Mac. And in fact, there are still 3 because the 3 serves completely different purposes. And it might also evolve like that for quantum computing. Maybe neutral atoms will be very good at a certain type of calculation, but photonic will be extremely good at another. And people are interested in the two fields. So there will be two technologies co-living in the different application niche, let's say. So now let's focus a bit more on Pascal technology, even if we stay at a very high level. So the heart of a Pascal quantum computer is a vacuum chamber in which you have in suspension some rubidium atoms, which are trapped by a series of optical tweezers, which are, which are represented here with the white laser. And then once they are trapped in place, with a second row of lasers, here represented in red, you are going to modify the quantum state continuously through time in order so that the combination of how the atoms are disposed inside your register and how you make the quantum state evolve, the final state of your system is going to encode the solution of a problem you are trying to solve. And you retrieve this information thanks to a camera which is taking a picture of the final state of your system. So this is a very high level representation of what a Pascal QPU looks like. The reality is that this very simple laser, which I'm saying, oh, okay, it's just a laser, you shine it on a mirror and it has all the good properties in order to trap the qubits. It's the majority of the Pascal technology is how to have extremely precise and stable lasers in order to trap the atoms and to excite the transition from one non-excited state to the other. And it is extremely complicated, and it's a real technological prowess to be able to do that. So not just to be only focused on what is happening on the vacuum chamber. In Pascal, what we believe is that the future of quantum computing is not going to be from the get-go full quantum algorithm. What we believe is that we are going to go through a period of time where quantum computing will fill a bit the same niche as what the GPU did, basically. The GPU, they did not replace the CPU. They were just extremely dominant at doing very specific tasks, which happen to be very useful for a lot of people. And in fact, on those specific tasks, the GPU completely replaced the CPUs. And this is what we believe is going to happen with quantum processing unit or QPUs. The idea is that there are certain tasks that are extremely complicated to do with classical computer. For example, problems on graphs that we are going to talk a bit later, which are NP complete, and there are really no good way to solve them efficiently with a classical computer. And the problem is that that kind of problem can be found in a lot of, how could I say, real life problems that you would like to solve for business purposes or scientific purposes. And what we believe is that when you're going to have complicated problems to resolve, you are going to have some sub-problems that are going to be sent to quantum processing units and then sent back in the workflow of an HPC center to be solved by CPU, GPUs, or anything classical. And this is how it will evolve at the beginning, really QPUs performing very specific subtasks much more efficiently than what classical computers could do. So what are the fields where we believe that quantum computing is going to be impactful first? There are basically three fields where we believe that, and this is not just Pascal point of view, it's the whole quantum community agrees that this is basically the three fields that are going to be impacted first. So at the beginning you have, you have optimization, which is so quite easy to understand what it is. You have a very big set of possible configuration, and you want to find the best solution given certain criteria in this multitude of possible solutions. You have simulation, and especially quantum simulation, which is basically when you want to simulate atoms, molecules, or anything that is going to exhibit a quantum behavior, it is extremely complicated to simulate with classical machines. Why? Because you have to take into account a lot of different stuff, a lot of different interactions, and quickly the complexity of doing that kind of stuff explodes. And so there was even Richard Feynman, which is one of the father of the quantum mechanics, who thought even in the 60s that it could be one of the application of a dreamt quantum computer. It would be to simulate how nature works. And so the idea would be to do some simulation of materials, of drugs, of how drugs behave, of how molecules behave, because these are simulation at a quantum level, and it would be tremendously more easy to do with the quantum computers than with the classical computer. And lastly, you have machine learning, which is basically you have a big buckets of information, and you want of data, excuse me, and you want to extract information from all those data and use it to predict trends or patterns. And the idea is that you have certain ways to do machine learning with the quantum computers that could be helpful for specific tasks. Whoops. No, it's okay. One last thing I wanted to talk in the presentation of Pascal and its technology before diving a bit deeper into the science meat of the topic today is Pascal software stack. This is something we are extremely proud of at Pascal. We are a full stack company, and we are building the software that is in order to use our hardware. So what you see here at the level of the lowest level is that we build either QPUs or emulators which are going to reproduce on classical machine the behavior of our quantum computers. But in order to communicate with those computers, we have developed first quantum software development kits and quantum application. Quantum software development kit, you could call that a middleware, where it's basically you are using a language to really speak to the quantum processing unit and say, okay, I'm going to want these atoms to be there. I'm going to want to program these pulses with that frequencies, etc. And it's going to provide a friendly environment to code on a Pascal QPU. And even higher than this middleware, you have the quantum application that we are currently developing. And it is libraries where we try to completely evacuate all the physical stuff behind the QPUs and to really focus on the mathematical formulation of your problems. And for example, there is already 2 available libraries. So the maximum independent set and the QUBO libraries for quadratic unconstrained binary optimization problem, where you can just enter the mathematical data of your problem. For example, for a maximum independent set problem, you just enter the graph that is representing your problem. For a QUBO, you just enter the matrix representing your problem. And then there is, everything is done under the hood to embed the problem on our hardware machine, and then to push you back the solution found by the machine. Of course, this is at an early stage of development, those libraries, but it allows you to really put a first foot in the door, let's say, in using a quantum processing unit. So this is the end of my presentation of Pascal and its technology. Do you have any questions? I'm listening.
Yes, there is a question from the audience for you specifically, since you mentioned that you worked previously for ANSYS. They were wondering if you have, if you're aware of them having any demonstrators or prototypes that perform simple ANSYS simulations within a quantum computing framework.
Okay, so I think my answer would depend greatly on what do you mean by a demonstrator? Meaning that if by demonstrator you're saying, okay, we have, for example, we have taken, so to give you a small idea, one of the two main stuff I identified as something that could be improved by quantum computing was in computer assisted engineering. Sometimes when there is an algorithm or a product called mechanical at ANSYS, and one of the step of this product is to do a mesh of complicated objects, and then when you have a very fine mesh, to portion it in order to be able to do some calculation on it, and then to I'm not sure what is the word in English, but to decoarsen it. And in fact, those kind of problems are very basically related to graph problems, and in particular, max cut problem. And those kind of problem, max cut problem, are NP complete problems. And this is where the bottleneck happens in ANSYS algorithm. When you have a big mesh, when you go beyond 10,000 nodes, this is where the main time is going to be spent. Of course, they have classical heuristics in order to do the calculation faster, but they would have been really interested in saying, okay, is it possible to have a better solution, or is it possible to have a faster one? And not even to put into production right now, even if they would be very interested if it was possible, but just, okay, we have a quantum computer and we see maybe it's not commercially viable, but we see that we are able to do something better or faster. They would be extremely interested. And if by demonstrator you call that, okay, we began to try to really code some stuff on quantum computers for those bottlenecks, yes, it was. If in demonstrators you mean we reach some kind of advantage with them, then no. And maybe it has been since, because I left 1 year and a half ago. But it was clearly in the process of doing so. And from what I remember, I saw on LinkedIn a publication very recently where they tried to do a quantum lattice Boltzmann. So it's kind of a fluid dynamic simulation. It was the other stuff I had identified. And on this topic, they had begun to do some tests quite seriously and publish some papers on it. Are there other questions, Christian?
Thank you for that. I will be answering in the chat the other questions for now,
Okay.
so you can continue.
No worries. So now let's talk a bit more about quantum computing and quantum algorithms. First, I want to do a small warning before anything. Is that I don't have the time to teach you quantum mechanics. It is completely inconceivable to even give a class of quantum mechanics in only 2 hours, let alone a subset of 2 hours. So I will try to give only the absolute, I will try to give the absolute minimum you need in order to be able to understand what to do with a quantum computer. This is a complex topic that requires like really a lot of time and investment, and also for those who are not mathematicians at heart, a good mathematical background. And if you are really interested in that, one of my preferred reference book, the one with which I learned quantum mechanics, is the one I put right there. What I want to insist on is that you don't need to read all this book in order to use a quantum processing unit. This is the goal, by the way, of building a full stack. The goal is to just alleviate as much as possible the complexity of all the physics behind a quantum processing unit. When you code on a classical computer, you don't need to take a Boolean algebra class. You don't need to understand how semiconductor works. And the goal from Pascal is to have the same level of abstraction for coding on a quantum processing unit. Of course, we are at the beginning of quantum computing, and so we are not as developed or as high level and abstract than what has been done for 50 years on classical computers, but we are really trying to alleviate as much as possible from the gritty, nitty-gritty details of the physics behind our machine. So this is going to be mainly all the quantum physics that you are going to see today, and it is going to be about qubits. Why qubits? Because it is the simplest quantum system that exists. It lives basically in a two-dimensional space with two basis states. This is called 0 and 1. And so it is very analogous to what a classical bit is. A classical bit, it has two possible states, 0 or 1. And by analogy, we have defined the two basis states of a qubit as 0 with this bracket symbolism where the 0 is put inside, and same for 1. And the main difference between a bit and a qubit is that for a bit, you can either be in the state 0 or the state 1. There is no in between. You are either on 0 or 1. Whereas with a qubit, you can be in any superposition of the two basis states, 0 and 1. And in fact, there is, when you are going to look at your qubit, there is going to be a probability to measure the qubit in a particular state. And the coefficients, like the probability of measuring your qubit in either the state 0 or 1, is going to be used to describe, in fact, the state of your qubit. So psi, the state of your qubit, this is how you define, okay, I have a state psi, is going to be equal to a certain scalar alpha multiplied by the state 0 and a certain scalar beta multiplied by the state 1. And those two coefficients are needed in order to describe the state of the qubit. A small parenthesis for people who are a bit savvy with mathematics. This is exactly a vector space. Your qubit is living in a two-dimensional vector space with the two basis states, 0 and 1. And this is why we speak of superposition, in fact. You are in a superposition between your first state 0 and your second state 1. And for those a bit less savvy in mathematics, it would be like if you are looking at a plane and you have the horizontal vector and the vertical vector. You cannot you can be on more than just the horizontal line and the vertical line. You can be on any point of the plan. And in fact, it's going to be exactly the same here. You can be in a combination of I am somewhere on the horizontal axis and somewhere on the vertical axis. And it is, once again, very related to the notion of vector space. But so I was saying that two coefficients are needed to describe the state of a qubit. And the very interesting thing is that when you go up to 2 qubits, you are going to need 4 coefficients. So here, let's say we have 2 qubits. You have 4 possibilities. You have 0, you are on the state 0, 0, or the state 0, 1, or 1, 0, or 1, 1. And so once again, if you were with 2 classical bits, you would only be able to be in the state 0, 0, or 0, 1, or 1, 0, or 1, 1. Here, you can be in the superposition of these 4 basis states. And this is why it begins to be very interesting, is that this can be generalized for a system of n qubits, meaning that the number of basis states for n qubit is going to be 2 to the power n. But if you need 2 to the power n basis state to describe your system. It means that you need 2 to the power n coefficients to describe your system. And whereas with classical bits, you would only be able to switch between each of these 2 to the power n states, here you are in a superposition of all those states. And you can make operations, you can design algorithms that are going to act on all those coefficients, alpha, beta, gamma, delta, and all the way around, and to act on all these coefficients simultaneously. And this is where you can already kind of grasp a very fragment of why quantum computing can be very interesting. It is that you are going to be able to do in parallel a calculation on all those coefficients at the same time. And so this is where we arrive to quantum computing and how, so it's been basically 5 years I've been trying to define quantum computing to in order to vulgarize it. And I think I arrived to something that is quite satisfying for me, is that the first part is that a computer, just a computer in general, it's a machine that manipulates data according to a set of instructions, which is the computer program. And in fact, a quantum computer, it's exactly that, but it does it on quantum data, meaning that it's data that is behaving as we have seen in the previous slide. And so the result of one iteration of computation, which is called the shot in the quantum computing ecosystem, gives a non-deterministic outcome. If you remember here, I told you that when you have this qubit, you have a certain probability to measure it in 0 and a certain probability to measure it in 1, which are linked to the coefficient alpha and beta. And so it is necessary, what interests you at the end of a calculation is to go up to the real state of your qubit or your ensemble of qubits. What you're interested in here is, okay, I would like to have a very good idea of what is alpha and what is beta. But when you do only one iteration, what you're going to measure is, okay, I found 0 or I found 1. And in order to really have an idea of alpha and beta, you are forced to redo the same calculation over and over in order to reconstruct your quantum state, in order to reconstruct your parameters alpha and beta. And so it is necessary to redo a certain number of times the same calculation to reconstruct your final quantum state, which is the thing you are really interested in because it encodes the solution of your problem. But you don't have a direct access to your quantum state. You can only, if I can use an image, you are only at each time seeing one possible realization of your quantum algorithm, and you have to redo it a certain number of times. See, okay, 50% of the time it's going to give this possibility, 30% of the time it's going to give another possibility, and that gives me a good idea of what my quantum states at the end of my calculation, but just before the measurement, is going to look like. And so the conception of a quantum algorithm, in fact, you can see it as designing a process that will amplify the probability of the desired outcome, of the one which are encoding the solution of your problem, while diminishing the probability of all the other events. And so this is what it means to do quantum computation. You are trying to encourage some probabilities to show up more than others. If you are looking for more information on quantum computing but don't want to mess with all the quantum mechanics behind it, this is the reference book that I put you here on the right, the Nielsen Schwang. Basically, it has 20 years. It's still, I think it's the only book with the that is as cited as the Schur article in our field in quantum computing. It has 20 years. It's I think I haven't seen one paper in quantum computing that isn't citing the Nielsen Schwang. It is very interesting, very well designed, meaning that there is a lot of stuff inside. I haven't read it in its entirety, but I often have to look at it and to look at some of the chapters, and it is very well constructed so that you have all the information you need inside each and every chapter. So good publicity. It's available in all your good libraries and on some dubious internet sites. So now I'm going to explain to you how a shot, so what I described to you just before, actually works in a Pascal quantum computer. And I'm just going to look at the time. Okay, still have half an hour, so we are good. And what I'm trying to explain to you here is the physical stuff that are going to happen in one Pascal quantum computer. Because from a personal point of view, I really find much more easy to have a grasp on what is happening in theory on my code if I know what is happening in the computer. Like I really enjoyed, for example, recoding some small, very, very small and basic computers with just logical gates in order to really have a grasp of, okay, this is how you go from the very basic element to something a bit more abstract and a bit more complex. And this is what I'm going to try to do here in a very high-level manner. So basically, what you have, the core of Pascal computer is the register. The register is an ensemble of qubits, and it is not permanently bit, meaning that the optical tweezers that are trapping the atoms, at each shot, we are going to trap new atoms, rearrange them in a certain position, make their quantum state evolve through time, and then dish them, and begin all the process over again. Of course, this is how it is done now. We have a lot of plans to be much more efficient in our managing of our quantum resources, but it's to give you an idea of how it is done at a very basic level. So here you have on the bottom right the three important steps of doing a shot with a Pascal QPU. So first you have what is called register loading. Just excuse me. You have what is called register loading, meaning that you are going to heat some rubidium gas and put it inside the vacuum chamber. From there, you are going to activate your optical tweezers and to trap some atoms of rubidium inside those tweezers. The idea is that so each of those optical tweezers are lasers, of course, and each of these optical tweezers is trapping an atom stochastically, meaning that you have a certain probability for each lasers to trap a rubidium atom, meaning that, and usually it's around 55% if I'm not mistaken. And what did I want to say? Yes, so you are trapping these atoms, and after that you have some you have a certain shape that is not corresponding to how you would like to have your atoms disposed in space. So there is a second step, which is called subregister rearranging, where, for example, if what you wanted to have is this nice square of rubidium atoms, and at the beginning you had that, which is a bit more spread among your register. You have to really rearrange atom by atom your register. And so this is, in fact, the part of the process which is taking a lot of time. It can take up to 0.5 seconds. And after you have done that, the quantum processing, meaning that you are going to shut down the traps for a very small amount of time and shine lasers on all your atoms in order to make the quantum state evolve. This part of the process, which is the actual calculation, is going to take less than 100 microseconds compared to the 500 milliseconds that can take the subregister rearrange. And so once you have rearranged your register, you can do the quantum processing. Then you reactivate your traps. And the idea of the measurement here is that your traps are going to act normally on atoms which are not very excited, but they are going to act as a repellent for atoms which are excited, which are in the one state. And in fact, in order to measure your result at the end, it's very simple. You look at your register. If there is an atom, you consider your qubit is in the state 0. And if there is no atom, you consider that the result of your calculation is that the qubit is in the state 1. And of course, as it is probabilistic, the results of your measurement is probabilistic, you have to repeat many cycles, the same exact process, in order to do one realization of a quantum algorithm. So now, let me just go up to that. A small discussion on the physics on our system. One question that I have a lot of time, and this is why I put this slide up, is why do we use rubidium atoms? And why this one and not another one? The idea is that rubidium atoms, if you look carefully, are in the first column of the periodic table. What does it mean? It means that if you remember from your high school, in an atom, the electrons are organized in layers around the nucleus, and there is the outermost layer, which is called the valence layer. And for atoms in the first column of the periodic table, the outermost layer only has one electron. And so, in fact, it is easier to control the energy level of this electron when there is only one, and this is one we choose the rubidium atoms. And then after, you could ask why rubidium and not cesium and or all the stuff of the periodic table. There are more complicated and sometimes even historical reasons to why rubidium and not cesium, for example, because the people who founded the labs, which is at the base of Pascal, always used rubidium atoms 20 years ago, and so we are just building on this particular technology. And so, how are we going to encode an information into these atoms? In fact, the idea is that when the outermost electron is going to be in its lowest energy state, it's going to encode the 0 state. And when it's going to be in a very excited state, which is called the Rydberg state, we are going to consider it's in the 1 state. Why the Rydberg state is important? Basically, it is because of a phenomenon called Rydberg blockade. When you have two neighboring atoms, basically, when one is in a Rydberg state, it prevents the other from also being in a Rydberg state. And if you want a very inaccurate but helpful image, it's like if you have one atom that has its outermost electron very far away from its nucleus, it's kind of if it were blocking the other electron to be also far from its nucleus. It's preventing the two would bump into each other. It's, for physicists among us, it is horribly inaccurate. I'm sorry for that, but it's very helpful for non-physicists to have an idea that there is kind of a blockade. There is a prevention of the two of them being very delocalized at the same time. And this is what is going to create entanglement and interaction between two neighboring qubits. And yes, the last thing is that the interest of this Rydberg blockade is that it is a quite long range of interaction when we are talking about about atoms. Like, it can have an impact upon micrometers, which is extremely large, considering like an atom is like 10 to the power minus 10 meters. So the question is now, okay, we have these nice atoms, how do we make qubits out of them? So in order to make qubits out of them, we need a lot of things. We need to identify a 0 and a 1 state. For this, I already told you, the ground states for the 0 states and the Rydberg states for the 1 state. We need to be able to address transition between level 0 and level 1. And for this, we have built a technology based on lasers, where we are going to excite the transition from 0 to 1, and from 1 to 0, of course. We need to know where the atoms are, and for this, we have the optical tweezers that are trapping the atoms in place with some nice patterns that you can see on the right. These, by the way, are actual pictures taken in PASQAL QPUs. So it's really the position of atoms at a very small level. Like here you have the scale. We need to be able to produce entanglement between the atoms to have a kind of an interaction. And for this is the Rydberg blockade phenomenon that I talked to you about. And lastly, we need to be able to measure the system. And for this, we have some stuff that is not relevant in this session, but we have some fluorescence imaging in order to take picture of them. So now I'm going to talk to you about the difference between analog and digital, which are two different paradigms of doing quantum computation. So the first one, the digital approach, is something that you are maybe a bit familiar, because either you have already coded on a classical computer, or you have already coded on other quantum computers that use this paradigm. For example, if you have used Qiskit, this is probably something quite familiar that you are seeing on the left. So what is the interest of doing a digital, of doing quantum computing in a digital paradigm? The main advantage is that it is universal, meaning that whatever algorithm you can think about, you can realize it with a digital approach. The caveat is that in order to do something useful, you need a large depth of your circuit. The depth is the number of gates you have to put one after each other in succession, basically. To give you a rough idea, to run the Shor algorithm, which many of you, I think, have already heard of, basically, it's an algorithm that allows you to factorize big numbers into their prime factors. In order to run that kind of algorithm, which would be able to break the encryption the system of, for example, banks, you would need dozens of millions of gates in succession to each other. For the moment, in 2025, what we can do best without having complete noise at the end of a circuit is doing hundreds of gates. So you see that there is orders of magnitude needed of technological progress in order to do relevant stuff with the digital approach. Of course, you have some applications that are less demanding, but the real killer application, the Shor algorithm, is still very far away. And so there is an alternative approach that you can do, which is the analog approach. What you have to, as an idea, is that when you have gates, in fact, you have very small modification, very small in the sense, very local, both in time and in space. In space, because you are acting on only one, or sometimes two or a bit more qubits. And in time, because it is a very short operation. You want to be able to to transform the state of your qubit very fast. With an analog approach, you are not saying that. You're saying, okay, let's say that a good way to have an idea of representing what is an analog approach, it's like instead of having a lot of small gates dotted in your circuits, you have just one big gate that is entangling all your qubits at the same time. And so instead of having very small Hamiltonians from time to time, you have one big Hamiltonian which will continuously modify the state of your qubits through times. And the the drawback of this method is that you don't control everything in your Hamiltonian. I will explain soon what I mean by Hamiltonian. Basically, it's the ensemble of forces that act upon your system, and so that dictates its evolution. And with this approach, you are not controlling everything in the Hamiltonian. You have a certain set of parameters that you can play with. So what this means is that it is not universal. You cannot do whatever you want with a quantum computer, with an analog quantum computer. But the big advantage of using this method is that for the stuff that you are able to do, you can do it much better than with the digital approach for the moment, because the requirements are less stringent, and so you are able to really extract all the quantum computing power of your computer with that kind of approach. So I'm looking at the time, and I don't want to spend too much time on the two slides I'm going to show you. It's just to tell you that neutral atoms in general, and PASQAL in particular, it is a technology that allows you to do both. You can do both analog quantum computing and digital quantum computing. And of course, we are aware at PASQAL that in the long run, the real killer applications will come from digital quantum computers. And we are currently building the foundations on how to create a digital quantum computer. However, we do believe that quantum utility will come first from an analog quantum computer. And this is what we are focusing on, analog capabilities right now, and why we have sold analog quantum computers to both to all our clients until then. And so those two slides explain in a bit more details what we could do with how we could do a digital quantum computer at PASQAL. But so now I told you that we are able to act on the Hamiltonian. So this here on the right is the Schrödinger equation. I don't want to dive too much into the details of what it means, but here what you have to keep in mind is that the time evolution of your system is going to be directed by these parameters, the Hamiltonian, which is kind of all the different forces we applied on the system. For the physicists among us, if you remember like the fundamental principle of dynamics, it's a bit like all the forces that we apply on our system, and those forces are going to dictate how the system is going to move through time. And so the idea is, what are the parameters that are available to us in such in the analog mode of PASQAL QP? And in fact, here is what we can do with an analog quantum computer. You have three stuff for the moment that you can manipulate. So first, you can manipulate the geometry of your system. The geometry meaning, okay, how am I going to place my atoms next to each other? So you have a lot of different geometries that are allowed by a neutral atom quantum computers. And the other aspect of it is going to be the lasers that you are going to shine on your qubits in order to make the quantum state evolve. And so you are going to have two stuff available, the Rabi pulsation and the detuning. And so here, for trying to give you an idea of what those three terms are going to do, I'm going to try to give you an intuition of how it works physically. I don't want you to think of, okay, what is the sigma x, what is the ni? I want to give you an idea of what the three terms are going to do in real life with your atoms. This term, the Rabi pulsation, in fact, is just going to do for all your atoms, is going to add a channel, add a communication channel between the level 0 and the level 1. And what it is going to do is just to make a circulation of the population between those two states. Let's say you begin on the 0 state. What this channel is doing is just saying, okay, there is an opening between the level 0 and the level 1, and there is a transition between the two. And so you're going to have a circulation of your information between the level 0 and the level 1. This one, the detuning, is a bit different. The detuning is when it is positive. It is important. You will see later when Christian will give you the class. When this term is positive, it is going to make the qubits in the state 1 stays in the state 1. And so if you just look at those two terms, you're like, okay, there is a transition enabled between my level 0 and my level 1. And there is this one who, when it is positive, wants to keep the qubits in the state 1. So with those two, you are saying, okay, so all my qubits are going to stay in the state 1 after a certain time. And the last stuff is what is going to prevent that. Basically, the geometry is when I have two neighbor atoms, they don't want to be in the state 1 at the same time because of the Rydberg blockade that I explained you some time ago. And so you have those three effects: circulation between 0 and 1, want to keep the qubits on 1, and don't want to allow two neighboring qubits to be on 1 at the same time. And what it is going to do, it is going to minimize a certain energy and give you a solution to some problems you might want to solve with all the three terms put together. Of course, this is for annealing algorithm. It may be much more complicated when we move our system fast, and what I told you is not completely exact in those conditions. But given the exercise Christian is going to give you, this is a good way to try to represent yourself what each of those terms is actually doing. Let me check the time. I have still 10-15 minutes, so we are good. So what are the main algorithms that you can solve with the main problems that you can tackle, let's say maybe, with such capabilities? The first is the maximum independent set problem. So what is that problem? An independent set, so let's say you have a graph. So to remind you, a graph, it's an ensemble of nodes and some of them are linked by vertices. This is the base definition of a graph. So for example, here you have a graph, you have 1, 2, 3, 4, 5, 6, 7, 8 nodes, and some of them are linked by vertices. For example, those two nodes are linked, and this one, they are not linked. This one and this one, they are not linked. And so finding an independent set of vertices in a graph where not two edges, I'm sorry, I always in English confounds vertices and edges. I'm sorry, vertices is like a nodes and edges are the stuff that are between the nodes. I am really sorry. And so finding an independent set is a set of vertices or nodes in a graph where not two of them are adjacent. So for example, here, the two orange points are making an independent set because the two of them, they are not linked by one vertex. This one, for example, is also an independent set because you see that for each of the nodes, they are not directly linked by an edge. And so the maximum independent set is the independent set of the largest possible size for a given graph. And here, if you look carefully, you could see that there are two maximum independent sets, which are those two ones. And so the maximum independent set is of cardinal 4. And in fact, what you maybe don't realize is that finding the maximum independent set of a graph in general, it's a very complicated problem to solve with classical means. It is strongly NP hard. And so this is something that can be extremely interesting to be able to solve in a lot of cases, but you only have heuristics if you want to solve it in a classical computer. And this is the kind of problem that can be naturally encoded on Pascal hardware. The second main algorithm that you can use is quadratic unconstrained binary optimization. So a QUBO problem, once again, it's a combinatorial optimization problem with a wide range of applications, like clearly in finance, in economics, in machine learning, in basic math, in in telecommunication, in energy, you will always find some QUBO problems because it is some minimization problem. And a lot of problems can be reformulated in order to be expressed as a QUBO problem. And in fact, it is very structurally simple. It's basically a connectivity matrix. Yet it is, once again, very computationally hard optimizational problem. And once again, you don't have, for big instances, really like good ways, satisfactory ways to solve it with classical computers. And some forms of a QUBO, once again, can be naturally encoded into Pascal hardware. Of course, so these are the two most natural algorithms to encode on Pascal hardware, but of course, these are not the only ones. So you are able to do a simulation of quantum system. Here it is a tutorial that is available on the Pulsar tutorials about anti-ferromagnetic state preparation. And we are also able to do some quantum evolution kernel, which is a type of quantum machine learning, which is quite adapted to Pascal hardware. Excuse me. So are there any questions before my very short introduction to Pulsar and before doing a small break and giving the talk to Christian?
There were a couple of questions. I mostly addressed them in the chat, but I think it's worth repeating some of them out loud. One of them would be about the current capabilities of the physical hardware. So the current generation Pascal QPU, or how many physical qubits and what computational modes are available on that, and what is planned, let's say, for the next generation.
So basically for that, what we have sold to clients, what is available for clients is 100 qubits. This is the one we have sold to Gensi and the one we have sold to Jülich in Germany. What we have in internal capacity for really R&D purposes, right now it's closer to 200 or even a bit more qubits. And for the full roadmap, what we plan to do is to have up to 10,000 physical qubits by 2030 and up to 200 logical qubits for the same date. For the moment, there are only analog modes that are available on Pascal QPU. The next generation also will be only analog. It will be available in 2 years, if I remember correctly. And the second generation, after the one currently deployed, will have digital capabilities.
Thank you for that. Another question that just came in is about what you mentioned most recently about the QUBO problems and the fact that some QUBO problems can be formulated on Pascal hardware. Could you say a couple of words on what are the potential limitations for QUBO problems?
Yes, completely. Basically, the main limitation for QUBO problems is that we cannot naturally encode negative correlations inside the Pascal quantum computer. Because basically, you can encode with Rydberg blockade just the fact that two stuff cannot be in, how could I say? You can say that if I have an atom in the qubit in the state 1, it's going to discourage its neighboring atom to be in the same state 1. And it's going to discourage them less and less the further they are from it. So you can modulate how much you want to prevent two qubits to be in the state 1 at the same time. But you cannot modulate inverse force. You cannot modulate. If I have a qubit in the state 1, it's going to encourage its neighboring qubits to be also in the state 1. And so this translates into not being able to put negative correlation in a QUBO problem. So for the moment, what we have for that is either you ignore them, you put negative correlation numbers to 0, which is not too much satisfactory, or there are some reflections on how to encode that kind of problems into a higher number of atoms and of qubits in order to kind of recreate some interaction terms artificially with a bigger number of qubits. And yeah, last problems would be also that there are some interaction that are kind of complicated to put at the same time with how we organize our qubits in space. And it's a bit complicated to just explain them. Yes.
Thank you, Vincent. Maybe one more question before you move on to the last part. Would you mind revisiting a little bit how graphs or how you construct graphs from the atomic register representation? So how do graphs come into play with describing the atomic register? In particular, how are the edges interpreted or represented?
Yeah. Very good question. Basically, an edge between two nodes of a graph represent an interaction. And the way you are going to reproduce, to modelize this interaction is by putting two of your qubits close together, meaning that there is going to be an interaction between the two of them. And in the case of, for example, a maximum independent set, what you want in the solution of your problem is not to have two nodes that are connected. How you can reproduce that is that you are going to want as many qubits in the state 1 as possible, but with two neighboring qubits not in the state 1, not in the same one state. And how you can modelize that is that for nodes that are connected by an edge, you are going to put the qubits that represent those nodes close to each other so that there is a Rydberg blockade phenomenon between the two of them. And this is how you're going to encode the fact that there is an edge between the two of them, and so that you don't want both of them in a potential solution.
Yes, thank you for that.
So I'm going to very briefly do a small introduction to Pulsar. And I'm going to begin with by saying the difference with a digital language. So some of you, I have looked at the response of the questionnaire, have already used other languages for quantum computing. And probably most of the ones who have used the language have used Qiskit, which is a language of IBM. And here you might be waiting to see, okay, how am I going to program gates with what you just said, etc. And no, instead of learning how to design a sequence of gates, what we are going to learn with Christian is what mathematical objects you are going to program with Pulsar. So in quantum computing, you have the evolution of the quantum state is going to be defined by a Hamiltonian. And so you are going to learn what is a quantum state in Pulsar, what are the Hamiltonians that you can define in Pulsar, and how to program those objects with Pulsar. Like, how do you define a quantum state? How do you define the Hamiltonian? How to have the step-by-step guide in creating a program into Pulsar. And I want to do a small trigger warning. You can do much, much more than what we're going to present to you today with Pulsar. And just for the sake of simplicity and time, we are just going to show you a tiny, tiny bit of what is actually doable with Pulsar. But if you are really interested in that, you have free tutorials available on the internet, and you can go as far as you want in learning how to use Pulsar. So what I'm going to tell you now, like the really very basic introduction, is what are going to be always the 4 steps on how to design a Pulsar sequence, meaning, okay, how to design a quantum algorithm on a Pascal QP. So the first stuff is that you are going to be required to pick a device. So you can follow this very simple flow chart. So you want to run your quantum algorithm, but how do you want to run it? First, do you want to run it on a real QPU, on a real quantum computer from Pascal? If yes, you need to have credits in order to use one. So either you will have a Pascal Cloud account, or either you will be connected to, for example, the TGCC or ULISH HPC centers. By the way, I did formations on how to use the Ruby machine at the TGCC. So if you are interested, you can ask to the Gen C to share the classes I gave 3 weeks ago. And if you don't want to run it on a real quantum hardware, you have to think of, do you want to be constrained by a real hardware specificities? And you might have several reasons to want to be constrained, saying, okay, I really want to be as close as possible to the machine in order so that when I run it on the real hardware, it will give as close as a result as possible. But maybe that you don't want to be constrained by today's hardware. Basically, maybe you would like more qubits than what is already available. Maybe you would like longer sequences. Maybe you would like hardware components that have not been installed. And for example, being able to shine specific lasers on each of your qubits, which will be available in 2 years at Pascal. And so this is what you have to keep in mind first. Do I want to be constrained with real life specificity, or do I want to make a specific design for the quantum computer I want to run my algorithm on? Then the second step is to create the register. So here I put back the Hamiltonian of your system. So this is this part that you are going to build. The register, what does it do? It defines the position of the atoms. So you can either directly encode them from coordinates, you can reproduce them from common pattern like triangles, squares, or anything. And the position of the atoms that you have is going to encode the specificity of your problem. For example, if you have, a cubomatrix, the translation of your cubomatrix is going to be directly into how you are going to put your atoms close to one another. And what I want to insist on is that, in general, choosing the good register for a problem is very hard. And it depends on which application that you want to solve, how you are going to make some compromises. And the physical idea of creating this register is that the interaction Hamiltonian, so once again, this part, is to make some quantum states energetically more favorable or less favorable. And the one that you want to be more favorable are the ones that are going to encode the solution of your problem. The third step is going to pick the channels. So here it is this part of the step. And here picking the channel is not the omega t or delta t. It's really the sigma x and ni. And the idea here is that you don't have to think too much for this session because it will mostly be the same each time. What it does is that it defines the energy level that will be used in the computation. And so when you talk about a channel, it is characterized also by its reach or its addressing, which defines how many atoms you are going to target with a specific channel. If the addressing of a channel is global, it means that all the atoms will be shined the same way with the pulse you are shaping. And if you have only a local channel, it means that only a subset of the atoms are going to be targeted with these pulses. And today, if I saw it, Christian, we'll only focus on global channel, if I'm not mistaken. And so you have two types of channel. You have the Rabi pulsation, the one I told you about, this one, and the detuning, this one. And so I remind you that Rabi pulsation is about circulation of the energy levels, and the detuning is about keeping on the energy level 1 if your delta is positive. And the fourth and last step is going to simply add the pulses. So here, once you have defined the sigma x, the channel, you are just going to define the temporal profiles for the channels you added. And so, of course, some parameters of your device dictate what's allowed in a pulse and how it's added to a sequence. So, for example, the max value of the detuning of a Rabi pulsation, meaning that you cannot shine too much energy with a certain laser. You cannot do a pulse duration too short because the real lasers behind it have a reaction time, and so you have to take that into account. But it will be constrained by the parameters of the devices you picked. It is the end of my presentation, just in time. If you have any questions, you can ask them. And if not, we are going to make a very small break before giving back the talk to Christian. Christian, if there
Yes,
are...
indeed. So we did plan, let's say, 10-minute break, more or less. So everyone, please feel free to get up, stretch a little bit, get a coffee or a tea. In the meantime, if you still have questions, I'm trying to go through them in the chat. I also want to leave you with two important messages for the follow-up part of the session. So we will first make use of an open source graphics user interface called Pulsar Studio to demonstrate in a more interactive fashion how you could go about with quantum computing. So I will put the link in the chat. It is an open access tool, so you do need to create an account. The same account is also used to access the PASQAL community platform if you're interested in learning more about use cases, algorithms, applications, and also we do organize quite a lot of competitions there. You get access to all of that. For now, I will use the Pulsar Studio visual tool as a showcase, so you are welcome to create an account and follow directly or just follow the presentation for that part. And this will be followed by an interactive hands-on exercise as it was announced. And because this session is indeed quantum in practice. So as it was in the invitation, if you want to follow closely, it will be required for you to install a specific Python library, the maximum independent set library. And once that is done, we will be making use of very nice Jupyter notebook that we have created for this occasion. So in the chat, I also put in the link for a GitHub repository that contains the Jupyter notebook we will be going through. It should be public and accessible for everyone. So if you have a Python environment installed with the maximum independent set solver library available, then you're welcome to follow and explore on your site. Otherwise, you can just follow the presentation and the demonstration from my side, as well as I will be sharing my screen. With that said, we still have 8 minutes left from the pause. So let's pick up the second half of the session. As a reminder, so I put it in the chat, the Pulsar Studio, link to Pulsar Studio, which is graphics user interface, an open access tool that we are going to use for the beginning to see a little bit in action how typically we go about interacting with a neutral atoms type quantum computer, not necessarily one of PASQAL, any kind of neutral atom system, what will be the key elements in interacting with it. And then we will proceed to the practical aspect of it to go through the Jupyter notebook. So at least for those of you who have set up the Python environment. I put some recommendations also in the chat to be careful with the versioning, as both the maximum independent set and the Pulsar library have had an update last month, so not super recently, but a couple of weeks ago. So do make sure that your installations are up to date in your Python environment, especially if you have had Pulsar installed previously in the same environment. So let's start with the first part then. As I mentioned, with the same account, with the same access as the one you would need to create for Pulsar Studio, you also get access to the community platform of Pascal. So for those of you who are interested, it is community.pascal.com. Just to check a confirmation, you can see my screen, correct?
Yes.
Perfect, thank you. So once we start looking at the platform or the code, I will put on the full screen mode, so we can hide some of the unnecessary elements of my screen. But I just wanted to showcase that the same account that we use to access Pulsar Studio is used to access the whole community platform, which has a dedicated e-learning module with different lessons from the beginning, from the introduction that Vincent has also presented to you, all the way to the different algorithmic considerations. And it also showcases some of our most listened tools in terms of SDK and software development library. And we will be focusing on Pulsar Studio, which is an extension of our first and initial software library, Pulsar, that was created as an open source Python library to provide a low-level interacting language between expert users and the physical quantum computer. So the link I provided for Pulsar Studio should bring you to this Get Started screen that will either prompt you to create an account, or if you already have the account, you will be able to launch the platform itself. Once you launch it, so the welcome screen will prompt you to either create a new experiment or to load one of the predefined ones. So we have, for now, 3 examples in the example gallery that have their own Pulsar documentation as well. So if you want to read more on it, you can, or you can just launch yourself in designing a very new experiment. So the interface itself serves as a graphics user interface on top of the Pulsar programming language. But it was designed with the intention that for users, for typically mathematicians, physicians, data scientists, who are not necessarily at ease or not used to programming, especially programming in a Python interface on a very, very low level, it might be better to have a more visual representation of what is happening on a very, very individual or on a global qubit level scale for the system. So there are multiple windows. So the layout, the default layout might be a little bit different since I've already used the platform. It has essentially 5 different tabs that you can move around, separate, and collect together. One of the first main tabs is the register, which serves as the geometric component that will allow you to define where you want to have the optical traps placed in order to have your atoms for the actual experiment, for the actual computation cycle. You have the channel part, which will be the second component that will allow you to define how you are interacting with your system. And then you will have other tabs such as the histogram that will follow the evolution of the quantum information in your defined system through the defined interaction. It will automatically generate a pulsar code for you, so you don't need to write any code depending on the manipulations you are doing for the register and for the different settings. It will automatically create a code for you that you can just copy paste to your programming environment. You can also visualize, instead of histogram representation, a quantum state representation of how the information evolves. An important aspect of the whole platform is that by default, it is running on a local emulation. So the tool itself is using your web browser's available resources, the available memory and computational capabilities of the browser itself in order to run quantum emulations. So everything is happening on purely classical framework. This is the reason why you have this message on the top right that up until 6 qubits, so 6 atoms in the register, it is able to instantly compute the different quantum states. From 6 onwards until 12 atoms, it is capable of pre-computing the quantum states, so running on the backend the QTIP-based exact emulation in order to capture the quantum states, and then for you to be able to visualize the actual experiment. And if it hasn't changed, I think for more than 12 atoms, it will alert you that you won't be able to execute it, just to be sure that for all different navigators or web browsers, it can execute the experiment. As of recently, the tool has also been connected by the PASQAL Cloud platform. So in case you have access to PASQAL Cloud computational resources, either the emulators, depending on the project, or soon to come for the physical system as well, you will be able to run cloud-based executions starting from this platform as well. For now, we will stick to the local emulation that everyone would have access to it. An interesting part of the whole window is on the right-hand side. This will serve as our interacting interface and parameterization interface that allows you to define the different components that Vincent has already elaborated to you in his last section. So from defining the device, defining the channels, defining the register, and defining the pulses, all is featured here. So the interesting part here is that since it's built on top of Pulsar, it allows you as the user to work with either a predefined machine like a mock device or one of the digital twin representations of our physical machines. But the platform, much like Pulsar, the programming language, allows you to define your, let's say, customized setting. It allows you to tweak the energy levels at which the different interactions operate. It allows you to increase or decrease the atomic count and the different distances to be respected. So for initial experimentation, it's better to leave the parameters as is, but it can be interesting to see and stretch especially for resource estimation type activities, to understand what could be needed, what would be useful for a particular experiment. So to start and so design an experiment, we can choose different predefined layouts. So there was also a question in the chat about this. So you have some pre-configured available layouts, such as a rectangular layout that we can start with an amount of atoms that are left to the user, as well as the triangular layout, or circular. But from this starting configuration, what you will see is you will be able to then manipulate the individual atomic positions later on. So for now, you can start with any kind of starting position because later on you can come back and revisit the configuration. And then this changes the view to the actual atomic register view. So here, each node represents the trap placement, so where we are catching in a physical computation the actual atom in order to manipulate its energy level. And as you can see, this graph representation that was illustrated by Vincent is visualized here as well, with certain nodes, certain atoms having an edge, having a connection running between them, which is a reflection of the physical interaction between these atoms. So the dipole-dipole type interaction is represented as an edge. Moreover, the thickness as well as the numerical value is associated to the strength of the interaction. Essentially, the closer the atoms are, the stronger the interaction is. This will be something that's important when we start working with the Rydberg blockade phenomena, because excitation of certain atoms will prohibit other atoms to reach this excited state. This will be the core concept in building the experiments. What's interesting is that it is really a graphics user interface with interactive elements. So you can just pick up a single atom and move around to place it in different positions. So the configuration itself, as long as it respects certain machine specifications in terms of distance, it allows you to place the atoms in almost arbitrary positions. So if you move around a single atom, so a single position, you can see that if I start moving it close to another atom, there will be this dashed circle that appears, that the interface will prohibit you from moving the atom closer than a specified distance. So this is first and foremost to represent the physical condition that the traps need to respect physical distance to avoid any kind of interference, and for the rearrangement of the atoms once trapped, the optical tweezers to have sufficient space to move around the atoms in the register preparation. So this is how it is represented in the system, and it interactively does not allow you to place atoms in certain positions. And as you can also see, it automatically updates the connectivity or the interactivity between the atoms. If you move an atom too far outside, it will have no interactions. If you move an atom close to the others, it will start interacting with all the other ones. This is always the first component of any kind of algorithmic implementation. How you need to create the layout of your atomic register depends on what type of algorithm you are working with. If you are working on a graph combinatorial optimization problem, you typically want to have a Cartesian, so a physical representation of your graph realized by the atoms. If you are working on a QUBO type formulation, as Vincent has mentioned, you are encoding the QUBO matrix as a distance matrix for the atoms. So you have an extra translation step to go by. In other settings, the configuration, be it structured or unstructured, will reflect the type of algorithm you are trying to implement. Once you're done with the configuration, the next step that comes is to define how you will interact with your atomic system. Indeed, because the register itself just defines where you want to place your atoms. These atoms, they are in their ground state, captured by the traps. As long as you don't interact with them, they will just stay atoms in their ground state. They will not become physical qubits. They will become physical qubits once we start interacting with the system, exciting the system, introducing external energy driver in order to have the system evolve towards its final stable energy. How the system evolves, you have different options in the way of interacting. Once again, the platform, much like Pulsar, its core component, is designed to feature any potential capability of a neutral atom system. It can feature analog global interactions, such as the ones realized by the Rydberg channel on a global scale. This corresponds to current capabilities of the physical machine. It also features future capabilities, the local Rydberg channel, which is being introduced as an external module or an extra module to the system, or eventually Raman, local Raman channels that will pave the way towards how we will implement quantum logic gates on a physical qubit level. The platform itself allows you to experiment, but for our examples and for the current demonstration, we will stick to current physical machine capabilities. So we will mostly make use of the Rydberg Global Channel to make sure that everyone is seeing the same picture and we talk about the same example. You can click on a plus icon on the top to start a new experiment, and we will load the AFM, the antiferromagnetic state experiment or state preparation experiment. This will initialize for us a predefined scenario coming from physics, but with other potential interpretations and representations as well, representing this specific structured grid representation of the atoms and their placement. It also has a predefined and well-computed interaction available to the system itself in order for us to be able to play with it once again. And it appears I've been disconnected. Let me quickly reconnect once more. And no spoilers here. Okay, now it's much better. So in this scenario, we have 6 atoms defined in total. Therefore, the automated instant emulation is working on the browser resources. So we can just click on the play button on the top right part of the screen, which will launch the experiment and allow you to follow the evolution of the quantum system in, of course, a very slowed down fashion. So the time scale, the actual time scale in which the interaction is happening in nanoseconds. So the overall experiment lasted less than 1.6 microseconds in total. And you can follow what's happening on the register layout. So the whole screen turned purple, indicating that you are interacting with a global laser, so a laser light that is viewed by all the atoms in the same fashion. And you can also follow the evolution of the quantum state through the quantum emulation from both the state, the histogrammic representation, or the quantum state representation as well, whichever is more useful to you. Since we are dealing with an actual emulation, you are able to stop the experiment, even go back in time. You have this yellow slider that allows you to manipulate the time step of the experiment itself. So I think there was a question popping up about the automatic emulation. So the automatic emulation is automatic. You don't need to click on the button. You just need to click on the play button under it. The button on emulation will be highlighted once in your experiment you have more than 6 atoms. In that case, it needs to pre-compute, and so the button will work that as well. In case the play button is not working, you might have run into the same issue as me, that you just need to refresh the page and it should come back online. So what I wanted to mention here is that we are working, of course, with an emulation. Therefore, you are able to revisit the quantum states for each time step. For it, and yes, apparently multiple people run into the issue that there might have been a server reset. That's why we were disconnected at some point. So just refresh the page. It should load, it stores the current information of your experiments. So you should be able to reload it just as fine. Since we are dealing with an emulation-based result, you have access to intermediate quantum states and intermediate informations, of course. This would not be the case in a physical quantum system-based exploration. This is the main reason why in a typical development cycle, you use emulator-based resources in order to test the code and its behavior. Also, an interesting feature, since it is still a graphics user interface, is that at any given time, typically at the end of the experiment, you are able to visualize the potential quantum states and their probabilities. Moreover, if you hover the cursor over a specific quantum state or its histogramic representation, you can see on the register that certain atoms, certain nodes are circled with a smaller circle, and other nodes are circled with a larger circle. The smaller circle corresponds to the zero information, indicating that the corresponding atoms is in its ground state based on a measurement that was made. The larger circle indicates the atom has reached its hyperexcited Rydberg state. So the one information is measured potentially from that side. Since we have access to all potential quantum states through the emulation, we can revisit all potential combinations, and you can highlight and visualize what would be the result of the experiment itself. For each of the states to observe what is the obtained result. This is a very artificial experiment in a sense that the atoms and the traps were placed in specific locations and the interaction with the pulses with the laser was defined in such a way that at the end of the day, if you are working with a noiseless system, you will obtain two entangled quantum states, each with a 50% probability, representing the two possible configurations of the antiferromagnetic state. So the antiferromagnetic state is sort of a spin experiment in which the corresponding electrons naturally align in an alternating top-bottom spin position when exposed to such a Hamiltonian evolution. So you are expected to see an alternating state of zeros and ones, and which one of them you observe, it is entirely up to a coin flip in this case. So this is a purely fictive, and very orchestrated experiment, but this is something that can be used to look into larger scale and much more complex dynamics as well. One other feature that I haven't really showcased yet, but is important to keep in mind, is that the main component in any kind of algorithmic implementation on top of the geometric layout is to define how you interact with your quantum system. We will see all these steps in actions with the Pulsar framework. For now, with Pulsar Studio, I just wanted to highlight that this provides an interactive visual interface on both the register layout and how you would set it up. So you can physically move around the different atoms to specific positions, or you can select and highlight an atom, and on the right-hand side, you can define its exact coordinates as well. Both of them are possible, so you can really design your proper experiments with it. Similarly to that, with the pulse design itself, you are able to interact and define different types of waveforms in neutral atom setting, and especially in our setting, you are for now controlling different components. You are basically manipulating two particular parameters of the laser light, at least in global Rydberg channel. Parameters are the amplitude, so the main driver for the excitation, and the detuning parameter, so the negative term in the Hamiltonian, that serve as an alignment for internal frequencies with external frequencies. As Vincent mentioned, it helps drive the excitation if it's a negative sign, or stabilize the excited states to some extent if it's in a positive sign. The type of experiment that has been essentially created here with these three artificial blocks is what we call an adiabatic evolution of the system. In general, what we require of an adiabatic evolution is a main driver through the amplitude that starts from 0 or close to 0, reaches its peak at some point and then relaxes back to 0. So the system gets excited and then this external energy is diminished. Meanwhile, the detuning parameter is shifted from one signs, typically from a negative sign to a positive sign, to help stabilize the excited states as much as possible. This is to guarantee that at the end of the experiment, you will have a clear or close to clear picture and idea of how the excited part of the quantum state, so the one information, looks like. Interestingly, as part of the examples, you have the same experiment defined with a single pulse source for you that is called an optimal pulse that was orchestrated with more precise laser constraints in mind. As you can see here in the different interactions, there are jumps when the laser shifts from one to the other. This is typically not something that can be addressed with the physical lasers. There is always a slight transition time.
Christian?
Yes.
There was a question in the chat and I tried to answer, but it will be extremely simpler if you show it. What do the small and large circles around the atoms in the register window represent when I hover over a histogram bin?
Yes. So the small circles correspond to the ground state of the atoms. So the zero information that is observed on that particular qubit. The large circles correspond to the Rydberg excited state of the atom. That's why it's denoted by a large circle. Essentially, it is a very simplified visual representation of the outermost orbital, so the free electron that our rubidium atoms have, who are close to the atomic kernel when they are in the ground state, and very far from the atomic kernel when you are in this Rydberg hyperexcited state. Of course, you don't represent the actual Rydberg radius because then the drawing itself would be complicated and confusing. It is just a visual representation of the two possible observable states. So the zero ground state from an energetic perspective with the small circles and the one larger circles for the Rydberg type hyperexcited state. And as you can see, by default, both small and larger circles are featured because in actuality, all these atoms are in their superposed state in between 0 and 1. However, due to the particularity of the system, if for one of these nodes you make a measurement and say that this first one is in the 0 state, this will automatically determine the states of the other atoms as well, due to their entangled and connected information. Questions?
There is no other questions for the moment.
Okay, so finally, I did plan some exercises, but I think it will be more interesting to move on to the actual Jupyter Notebook-based demonstration. For now, I just wanted to showcase that it is really a platform for experimentation, exploration that allows you to explore different geometric configurations, different laser pulses, and all in this interactive, easy to understand, easy to follow way that automatically generates for you the actual pulsar code. So the Python code you would need to write and visualize yourself. If I make any kind of modification, let's say I'm moving around Q3, the fourth atom, it will automatically update the corresponding segment in my code. Similarly, if I were to change something with the pulse itself, it highlights for me where that specific laser pulse is defined, what are the different parameters with the applicable pulsar syntax, and helps you better navigate with your code itself. So it can be a very efficient tool in starting to learn the nitty-gritty part of very, very low-level programming aspect of manipulating neutral atom systems, and more importantly, manipulating quantum systems in this analog continuous in time fashion. So as you can see here, by default, you don't have any quantum logic gates. There are no elementary building blocks at your disposal. You are the one who is designing the whole interaction from the beginning until the end. So to move on, let's now switch to the prepared Jupyter notebook to get some more hands-on exercises. So I linked in the chat the GitHub repository. It should only contain a Jupyter notebook and an image just in case it is not loaded correctly within the Jupyter notebook. So hopefully it is working for everyone. And if you load it up, you should see something like this. So we prepared this Jupyter notebook exercise to go through some key elements with one of the particular messages from PASQAL side in mind, which is that our focus is to be able to reach and showcase quantum utility already with the currently available quantum systems. So as Vincent mentioned, our main focus for now is the analog, this for now global, soon global and local interaction of the atomic register to interact in this continuous in time fashion with our qubit system. And what we try to illustrate with these examples is that you can reach a stage where you are dealing with practical I would say real world problems, maybe not realistic size problems, but we prepared a couple of exercises that will illustrate how the different levels of interaction could look like. So for the first cell in the Jupyter notebook, it is just a quick check to make sure that the most recent version of the maximum independent set library is installed. So hopefully my Jupyter kernel is still working and I have everything installed as it should be. And for this initial consideration, what we prepared is a little bit of a showcase about graphs, about networks, about connection or similarity matrices, or about grids. You can really find very different names for it, and you can find very, very concrete practical representations of it, going from chemical molecules to a traffic network layout with roads and walkways, all the way to more abstract and artificial representations such as conflict graphs. From a classical perspective, I would say we don't really like working with graphs for multiple reasons. On the one hand, there is the algorithmic consideration that it is hard to create a uniform representation of a graph with classical storage and with classical computational phenomena. Indeed, how we store classically a graph is we use either the adjacency or incidence matrix representation of it, which depends on how you label the graph, how you index the different nodes in order to represent in a matrix form which nodes are connected with which ones. This representation is not unique. Therefore, any kind of method that works with this matrix-based representation of a graph needs to be able to recognize whether two matrix representations correspond to the same graph in actuality, which can be already a very challenging problem. On top of that, a lot of the optimization or combinatorial problems that involve graphs, even a lot of the machine learning considerations involving graphs are known to be computationally hard. So they do typically belong to the NP complexity of the consideration. So herein comes into the play of quantum systems that can alleviate this computational complexity through various means. And we will see different representations of the aforementioned maximum independent set problem, which will be our key component for today's exercise. But in particular, with an analog and with a neutral atoms type analog system, you have the added benefit of being able to encode unit disk graphs by default, and even larger families of graphs through graph embedding type methodologies. So to start off this exercise, I prepared some showcase on how classically, we would manipulate graph structures with one of the open source available Python packages called Network X. So Network X is mainly tailored for any kind of graph manipulation. So it is not a PASQAL package. It is a standard mainline optimization and combinatorial tool and package that exists as an open source and quite well optimized tool. And we will see that this quite well optimized is not super optimized in certain scenarios. So what I did for now, for an initial example, is I defined a very small graph structure that I created with 5 nodes in mind, index from 0 to 4. And then I created a couple of edges to showcase. And you have very, I would say, a large set of different draw commands available in Network X. So this already highlights the fact that how you visualize a graph is something that is not predetermined. So a graph structure, mathematically speaking, it is just a collection of nodes and edges running in between certain nodes. How you draw it out with Cartesian coordinates, how you represent it in the plane in this case, it is entirely random. It can be very flexible. For this reason, the default draw command, if you relaunch the execution of it, it will draw out the same graph in various different representations. Some of them are planar, some of them are structured, but it doesn't really follow any proper rules. For this reason, within the Network X package, they have defined different versions of the draw command that will follow some structural considerations to make sure that graph visual representations can stay consistent. But there is a full documentation on that. If you're curious, you can read on the various examples, or you can just play around with this same cell to look at the different Cartesian representations of the same graph. So all of these representations correspond to the same graph. It has the same nodes. The same nodes have the same connection in all these representation. To have a little bit of a more complicated, more interesting, or even more exciting example, I also propose to create a slightly more complex graph. This graph will have some labeled nodes from 2 different types. So it will have a click in it, so a fully connected component with 10 nodes. And it will have some 10 more nodes running as these individual extra elements. Once you create the nodes, so you can create it as individually, add individually, or add it as a list format. We will create the edges. So the click component will be a fully connected part. So we will have 10 nodes that will be connected with everyone. And you will have 2 nodes that will be connected to all the individual ones. And as you can see here, there is a specific draw command, the Kamada Kawai representation, which follows a specific type of pathfinding within the graph to create a visual representation that typically will stay the same no matter how many times you execute it. And so as a result, you will obtain this cute 10-legged octopus formation of your graph itself. So as I mentioned, you created a click. So these 10 nodes in the middle and on the top are fully connected. Everyone is connected with everyone else. And you have these 10 legs of sort that are acting as this independent set that is connecting to 2 of the nodes from the click itself. So again, this is just an example that was tactically chosen to highlight and illustrate the independency in order to introduce the maximum independence set problem in a visual fashion. So we will look at this graph first and foremost to revisit the different definitions. As Vincent has mentioned, the maximum independent set problem is one of the staples, one of, let's say, a hello world type problem formulation, especially for a neutral atoms type system. And to introduce this topic and explain why this is the case, why you can consider an MIS type problem the hello world of neutral atom systems, we want to go through a little bit in this visual aspect, the different definitions that go into defining what is a maximum independent set. The first component to this is the definition of what an independent set is. So I've provided the graph theory official mathematical representation, mathematical definition of it, but intuitively an independent set is a collection of nodes such that there is no edge between any two of the selected nodes. So as an example, we can highlight from the previous graph these two nodes on the side. So together, they form a subset, a subgraph that is an independent set because there is no edge running directly in between these two nodes. This is not the only independent set of this graph. Typically, a graph can have many, I would say exponentially many independent sets at its disposal. To go further and to also confuse everyone a little bit, in mathematics and from the combinatorial perspective, there are two possible problem formulations or problem statements that can be defined related to two specific mathematical constructs. Both of them refer to the extremity, the maximality of such a set. So these two definitions are the maximal independent set and the maximum independent set. And I will try to make sure to emphasize which one I'm talking about for this showcase. So first, the maximal independent set. It is an independent set that cannot be expanded further such that it still stays an independent set. So there is this maximality due to a brute force extension or the impossibility of a brute force extension. So to illustrate this, we have selected as the next executable cell this node here in the graph. It is an independent set. It is a single node. It doesn't have any connection with any other nodes in the selection because there are no other nodes in the selection. It is an independent set. However, this full node is connected with all the other sets, all the other nodes in the graph. It is connected to any other element of the clique by definition. And it is also connected to any of these outlying nodes. So you cannot add any more nodes in this selection such that it still stays independent set. Therefore, it is by definition a maximal independent set. This maximality highlights typically a typical shortcoming of any kind of greedy type method. So if you were to try to find with a greedy approach an independent set, depending on which node you start with, you might run into some very serious problems. Because clearly, even the previous highlight, the previous example where we selected two nodes on the side, it was a mathematically larger set, a larger independent set. But according to this maximality definition, this single node is a maximal independent set because you cannot expand it further. For this reason, there is another definition, and that will be the key construct for what's to come. So after this, we will forget about the maximality and we will concentrate on the maximum aspect of it. So maximum independent set is the largest possible independent set from a graph. So largest in terms of the size of the selected nodes. So it is from a global perspective, it contains the maximum amount of nodes such that there is a corresponding subgraph that is an independent set. So for this particular graph, we can define such solutions. For example, one such maximum independent set is selecting all the outlying nodes plus one of the nodes from the clique that is not one of the two nodes that is connecting with everyone. This also highlights an interesting feature that a maximum independent set is typically not unique. So from the clique up in the top, I can select any of the 8 nodes to accompany these 10 nodes on the bottom side to form a maximum independent set. So a maximum independent set is, in most cases, not unique. You can have many different versions of it. And as we have illustrated, finding a maximum independent set is not exactly easy if you go through the greedy approach, because we can run into some very serious issues. Instead of having one as an independent set that cannot be expanded, the actual solution for maximum independent set has 11 nodes in it. There is a very, very large difference. Of course, this graph is orchestrated in a fashion to illustrate that greedy approaches will fail. So it might not be the most realistic scenario, but it is something that is interesting to keep in mind because it will come back in a very concrete example. What is known about maximum independent set search? So from a classical point of view, from a complexity theory perspective, we know that it is, as Vincent mentioned, a strongly NP-hard problem. So to find an exact solution with classical resources, you require essentially exponential time. So you have the actual time scale for the best known exact method. For this reason, if you want to solve this problem from a classical perspective, you typically use heuristic approximate methods that are able to find a good solution without necessarily having the mathematical guarantee that it was able to find the best solution. Here comes into the play of a quantum representation to it. So with classical resources, we are limited from both a theoretical and a practical aspect. So can quantum help with this? And the answer to that is yes. So there are known polynomial time algorithms on pure quantum computers that can solve this problem. How you go about solving it? There are, I would say, two main ways currently with the consideration of different quantum systems. The generic approach relies on the fact that the maximum independent set problem as a graph problem can be reformulated as a cost function based optimization problem. And here I've given a quick extract on how you would define an objective function, a cost function that you need to minimize. And the solution of this minimization problem will be the potential representation of the maximum independent set problem. The connection here and how you introduce this cost function is through the formulation of this specific binary variable-based optimization problem without any further constraints. And so it is a specific type of QUBO, quadratic unconstrained binary optimization problem that arises through the association that for each node, for each vertex of your graph, you define this Z variable that can have two values, either 0 or 1, corresponding to whether you select it in your subset that you want to make independent or you do not select it. So it is 1 if it's selected, and it is 0 if it's not selected. You are aiming for a maximum amount of nodes selected. Therefore, the first component of this cost function that is being introduced, it is going to be the sum of these variables. So the sum of these variables, the larger it is, the more nodes you selected. With the negative sign, the smaller it is, the more nodes you have selected. So this is a quick and neat trick to turn a maximization problem into a minimization problem. So the first part of the cost function determines your objective. So you want to select as many nodes as possible. However, you want to make sure that these nodes form an independent set so that there is no edge running in between them. So how can you quantify that? You will quantify that with a quadratic, with the second order terms. So for each of the edges in the graph, if you have selected both nodes forming the edge, this product will be 1, so 1 times 1. If any of the two nodes of an edge are not selected, the product will be 0. Therefore, this sum can only take positive elements when you have an edge selected in it. And with this specific U term that you will probably want to make it very, very large, you will penalize your cost function. You will obfuscate the advancement of the cost function whenever there is an edge at its disposal. Therefore, any kind of optimization that aims to minimizing this function will try to have as many zi's, as many z's with the van value to keep it as negative as possible. And it wants to try to keep this term as close to zero as possible. So the best scenario is when it is zero. So you have an independent set. By controlling this U term artificially, you can emphasize more or less this independency criteria to relax it. So this is one way to represent a maximum independent set problem as a cost function based optimization problem. Once you're done with this, you can leverage many different classical or quantum enhanced optimization techniques to try to solve it. Classically, you will run into a similar issue that it is a discrete optimization problem for which heuristic methods work best because exact optimizers will struggle after a certain amount of variables. But we also have another way of looking at it, of addressing it. So this is something that is inherently specific to neutral atom systems. And this is what's described here, related to the graph representation, which in this case also allows us to highlight a very inherent connection with the Ising Hamiltonians that we will use to solve and drive the system. Indeed, this cost function representation is a very simplified way to describe and represent the acting Hamiltonian on the system itself, wherein the geometry itself is encoded in the second order terms. This is our case as well. Our atoms will form the nodes of a graph representation, and edges will correspond to the excitation. And through the adiabatic evolution, through the excitation, we will want to select, we will want to excite the system, and Rydberg blockade phenomena will occur between neighboring nodes, between connected nodes, and therefore this overall excitation, this adiabatic evolution, will naturally, will physically introduce a selection that will favor independent sets and that will favor large independent sets in actuality. So if I go back to my Pulsar Studio representation, so if we take a look at the very same example we illustrated previously, what I can see here is that I have a specific graph structure defined on 6 nodes, and certain nodes are connected with each other. My aim is to solve the maximum independent set problem for this particular graph. So what I want to do is first I want to represent my graph in the atomic register, which is something that may not be as straightforward as it is now, but we will see an example on that. And once that is done, we will excite the whole system through this global channel. So we are working in the purely analog setting to introduce this excitation to have the whole system evolve. This excitation will allow the atoms to reach this Rydberg hyperexcited state, and the Rydberg blockade phenomena will prohibit nearby atoms to both reach this excited state at the same time. For this reason, by the end of the experiment, certain atoms will reach and then stay in this high excitation state. So they will measure 1 in the readout, while all the neighbors will be pushed to a lower energy state. So they will be measuring 0. And indeed, the solutions for this interpretation are actually the 2 maximum independent set solutions of the graph representation. So the same problem formulation with different storylines can give rise to these different solution strategies for us, all through the adiabatic evolution itself. So I just wanted to showcase that from a physics perspective, the interference state experiment is in particular a specific representation of maximum independent set solution on a very, very structured graph. So to go back to our exercise itself, we will look at this problem from 2 different levels of interaction. The first level of interaction will allow us to work on a very specific graph representation. And this graph representation already is coming with its own geometric encoding. So we already skipped the first step and potentially the most complicated step in the problem encoding, which is how you translate your graph structure into the quantum system, how you represent it into a reasonable Cartesian system. So for now, for this first exercise, we prepared a couple of lines of code for all of you to experiment on how, on a very, very low level, you would implement the core component, which is creating the atomic register. Once you know how your graph should be encoded, how it should be represented within the quantum computer, and then excite this system with a very, very simple adiabatic evolution in order to check whether you have indeed solved the problem or not. So these couple of lines of code help you guide through this initial component. So we created this 5-node graph. This was our first example graph, and that we draw out with network X as well. So we are going to recreate the corresponding atomic register and launch a simple adiabatic evolution on top of it. So to load the packages from Pulsar for this lower level interaction, you can just execute the first cell. Hopefully everything is working as intended. The first part of the exercise will focus on you recreating the corresponding atomic register itself. So it boils down to essentially defining the different nodes. And you can do that, for example, by associating the corresponding coordinates as well. So from the Pulsar Studio example, you can cheat and look at the exact syntax. Or if you wait 1 minute, I will also provide the example as well. Hopefully I will not type anything wrong in. Or I can just cheat and switch to my solution sheet. That will be even easier. Oh. In the interest of time, probably we will go that route. Again, so for this first exercise, all you need to do is, yes?
There is a question that I think would be easier to respond by voice. Are all graphs representable in the register? The interactions between the atoms seems to be related to proximity.
Yes, correct. So it is indeed a distance-based interaction, and therefore the associated graph structures that naturally arise from any kind of atomic register representation are also distance-based, meaning that these graphs have a representation with Cartesian coordinate system, in a Cartesian coordinate system, in which below a certain distance, all nodes need to be connected with an edge, and above a certain distance, none of the nodes can be connected by an edge. So this is what we call a unit disk graph. When any graph admits such on Cartesian coordinate system-based representation, it is called a unit disk graph. So this is a particular category of graphs. It is not every graph can be represented in such a fashion. There are very easy examples to construct. Most of the graphs, especially from practical problems, when your network, when your graph formulation arises from a grid, from a physical construct, or from units defined on a map, they typically correspond to a unit disk graph. If that is not the case, you have specific graph embedding techniques, graph combinatorial tools that allow you to introduce extra nodes and maybe extra edges to rewrite your initial graph with a new representation that itself will be a unit disk graph. So this is something that we know from a theoretical perspective that in case you are allowed to work in 3-dimension, so currently and so far we have only worked in 2-dimension, but if you are allowed to work in 3-dimensional graph structures, any graph, any given graph can be represented by a unit disk graph extension. In case of 2-dimensional projection, there are certain limitations that require you to do some either artificial approximation or some graph decomposition techniques to have unit disk subgraphs addressed with the system itself. So there are different workarounds. Not all graphs can be natively encoded. This is what we alluded previously as well, so that this can be the bottleneck of the problem. For this exercise, we are just focusing for now on this current given example.
Just Christian, will you talk a bit about QUBO solvers and or MIS solvers?
Yes. So the second exercise, it is about the MIS solver indeed. So for this initial exercise, what we planned is to expose to you how, in a very, very low level, in a very, very engineered way, you would go about solving an MIS system with a specific graph representation. Nowadays, you have access to software tools that allow you to automate most of these procedures. So the exercise 2, you can already spoil yourself. Exercise 2 is based on the maximum independent set library, which we ask you to install to follow the exercise. And we will go through and see actually how high level this implementation can be made. So you can automate most of these procedures. It is interesting to see both levels. So this very low level interaction that helps you maximize the utility and the capabilities of the quantum system. And we will see on the second exercise a very high level representation that automates everything for you so that you can make it accessible for people who have never heard about quantum computers even. And so there was also a question about the QUBO solvers. That is also the case for QUBO solvers. So we did not prepare specific exercise for this session because it is already quite time-consuming to introduce the graph combinatorial aspect. But you can follow a similar logic with this as well, that you can build from the ground up using low-level interactions, a very tailored representation, so an atomic register representation of your QUBO matrix, and then introduce a meaningful excitation, again, an adiabatic evolution, to solve your QUBO problem with that specific cost function. Or there is also a QUBO solver from PASQAL side as well. We have an open source QUBO solver available that automates all this procedure. And it is enough for you to just define a matrix and ask the QUBO solver to solve that, that system with the matrix definition. So to move along, this first part, it was really just to create the register itself. Again, you can label the nodes if you want, and if you execute the next cell, it will draw and visualize the same interaction. You don't really need to label them. You can just input the coordinates in a Python list structure and feed it to the qubit structure to create the actual register. For the register generation, there are also predefined commands that use existing layouts. So if you want to use a triangular, circular, or a rectangular predefined layout, you can preload such layouts with the specific commands as well. For this exercise, I want to just showcase the part that you really can flexibly place the atoms themselves in particular positions, as long as you respect the distance constraints. So here, this is something that is also visualized. The second exercise, and I almost spoiled the solution there, is about working with this graph to find what are the maximum independent set solutions to this. So what are the largest subsets of the nodes that are still independent. And as I mentioned, typically maximum independent set solution is not unique. Indeed, for this graph as well, if you start looking through the different combinations, you can quite easily see that 3 and 4 are in a good position to be part of it. And you can add either node 1 or node 2 to the set to form a solution, form a maximum independent set. You will never be able to have four element independent set due to the presence of this triangle, so a fully connected 3-node block in it. But a 3-node independent set, you have 2 of them, so 1, 3, 4 and 2, 3, 4 are both solutions to this problem. In the interest of time, we can quickly go through the second element, and I can also spoil you with the actual solution. The exact meaning of this exercise is to see that once you have done the register design, you need to create an interaction with the system. So we will be building together on an adiabatic evolution of the system. And this adiabatic evolution is based on certain geometric considerations. In this case, we are given a good geometric representation of the graph. Therefore, we can just compute the different distances. So we are interested in the maximal distance where we have connected nodes, which will be between 0 and 4 and 0 and 3. This will be the maximum distance of 10. And we are also interested in the minimal distance of not connected nodes, which will be, if I remember correctly, between 2 and 3 or 1 and 4. These two quantities can be used to define values of the amplitude, which scales 1 over the distance to the power of 6 with a specific coefficient. So we can use this to frame and determine quite an optimal value for the omega, for the amplitude parameter, which will serve as the driver, as the main component of the excitation itself. Here we choose a value that is halfway between the minimal and maximal advised value of this amplitude based on the geometry of the graph itself. So once you define these two distances, so 10 and 13.6, around 13.6, you can execute the cells to create the base parameters, for which the next exercise asks you just to define an interpolated waveform, so an interpolation type laser sequence for both the detuning parameter and the amplitude parameter as well. So a typical syntax of any pulse, any kind of laser pulse, is that the first coordinate will define how the amplitude parameter, so the omega parameter, evolves over time. So in this case, an interpolated waveform is used. So an interpolation type waveform will be defined over the course of time t. So here we fix the t as 4.5 microseconds. And what we expect is for it to go from 0. In actuality, it is better to leave a little bit of leeway. The algorithm itself, and especially the emulation, will work much better. But technically, it goes from 0 all the way to the maximal value of the amplitude, and then back to 0. The second component is the detuning parameter that will go from its initial negative value, so the starting point, go through 0 and then evolve to its positive value. You can give different values to it. I've given some indications on how you would choose it. You can work on different ways to optimize it. So there is not necessarily a golden rule with this. The baseline is that you want to end up at the end of the day with such a type of waveform where you have an amplitude parameter going from 0, or in this case close to 0, reaching its maximum value, then relaxing back to 0. And the detuning parameter, so here the purple side, is switching signs from a negative value to a positive value. And in this case, the interpolated waveform puts the simplest representations to it. So quadratic curve for the amplitude and the linear evolution of the detuning itself. And once you are done with the pulse sequence itself, you can just simply execute the next cells that are here to actually launch the experiment on an emulator. So you are working on an exact emulator. In this case, the install size is quite small. So you can work, for instance, with Q-tip emulator, which is built in as part of Pulsar. So you define for the emulator the actual laser sequence that it needs to execute, and then to just run the run command to get the results themselves that you can recover in different formats. And we also provided handy quick visualization to illustrate some results from the actual emulation. And what you can see here is that from 1,000 shots in total, you have 2 quantum states that are featured quite often. So the 0, 1, 0, 1, 1 corresponding to the selection of the 1, 3, and 4 nodes. If we go back to our graph representation, 1, 3, and 4 was one of our maximum independent set. The second most likely in my case is 0, 0, 1, 1, 1. So the second, third, and fourth atom or node being selected. So this is a typical interpretation of the results themselves, that atoms that have reached this high energy Rydberg state will be in the 1 qubit information for the measurement, and they will correspond to a selection of independent sets or close to independent sets, depending on how well you manage to set up the adiabatic evolution. And as an exercise, just as a tool that can be handy, and we also provided a quick script that allows you to test for different parameters of the system. So in the definition of the lasers, the pulse signals, we fixed a lot of parameters. We fixed a delta value, we've chosen an amplitude value as a middle point. We have chosen a specific time frame, but all of these choices may appear arbitrary. So in a typical engineering, this is when what we call the pulse shaping starts, when we try to optimize this pulse sequence to get the best quality results possible. And this last part of the exercise focuses on the script where it runs through different time scales for the evolution, going from 1 microsecond all the way to 10 microseconds, and quantifies how likely it was for you to capture the 2 maximum independent set solutions. And as you can see that you have this curve in low time frames. So when you have 1 or 2 microseconds for the evolution, in fact, the evolution is too quick for the quantum system. It happens too fast. It doesn't have enough time to reach the excited state and keep the excited state. So the quality of the solution is quite bad. And what you can also see is that around 5 microseconds, it starts stabilizing, and you have a close to 1 probability of capturing at least one of the 2 good solutions there. So a good stopping point to not to use too much the quantum computer is around 5 microseconds. So we had 4.5 in the experiment, so we were already close to optimal. But you can run this script by testing different parts of the parameter on omega, on the delta, on a combination to try to identify what is the best interaction for this particular system. In general, your objective would be to make it sufficiently specific to a type of instance without being too specific to a particular instance of it. With that said, I'm aware of us running out of time, so I just wanted to quickly go through the second exercise we prepared, which showcases a similar example, but from a much more higher level perspective. So we defined a very, very simplistic, but quite realistic problem that may arise whenever you are dealing with any kind of installation of Python libraries and conflicts that may arise due to certain libraries being compatible with certain versions of Python but incompatible with other versions of it. So we defined a very specific simple scenario for you in which we have 5 Python versions as available, and we have 2 libraries that we want to install, and we want to install them at the same time. So we need to find a version of Python that is suitable for all of them. So this is typically, I would say, simplified but real-world problem that does not directly lead to a graph representation, but can be featured to introduce what we call conflict graphs. So indeed, if you consider all the different versions and the libraries as nodes, you can draw edges in between the nodes whenever there is an incompatibility between them. So incompatibility can mean that you cannot have multiple versions of Python installed in the same environment. So all these Python versions and the corresponding nodes will be conflicting with each other. And you have instructions from the description that these two libraries, migrate library and another library, are conflicting with certain versions of it. So with these two nodes, it allows you to draw out a specific graph structure. So I've left some empty cells for you to draw it out on your own, but you already have the solution also available for you with the necessary labeling. So if you go around with this graph representation, you obtain the different Python versions in this full connected click. As I said, we cannot have multiple versions installed in the same environment. And then you have conflicts from the two libraries you want to install. And now the problem you are looking at is trying to find a good Python version that will not conflict with any of your libraries. So this is something that will be at some point tied to the maximum independent set type problem. For now, let us look at this from a graph perspective. So the second question in this exercise just asks you to identify what could be a good independent set and maximum independent set solutions of the graph. So if you haven't realized it yet, this is a simplified version of the second example graph we introduced, the 10-legged octopus representation in the beginning. This is 5 + 2 node equivalent of the same structure of graphs. And similarly to that, we know that the solutions to the problem in terms of maximum independent set will be a collection of these external nodes, so different libraries, plus a selection of one of the nodes in between that is not connected to either one of them. And indeed, this selection, so selecting a maximum independent set, will contain all the necessary libraries, plus a version of Python that will not conflict with any of them. Therefore, if you are able to identify a maximum independent set, from that, by excluding the libraries mentioned, the remaining node that is left over is a non-conflicting Python version, which will solve the problem. So with this extra consideration, you can actually solve the problem itself. I also highlighted here quickly that yes, you do not need a quantum computer to solve this problem. You can solve it on paper. The idea is to highlight the different methodologies that go into this. And in particular, interestingly, the maximal and maximum independent set commands from the network X package, so the aforementioned available and streamlined, typically used graph combinatorial toolset, might not be the best solution. So in my previous execution here, are my maximal independent set finder run into the same issue we run previously, that it managed to start with the node that cannot be expanded to stay independent. And even the maximum independent set finder, because it's approximative, it cannot do an exhaustive search. It tests certain combinations by default, and it ends up with an independent set that is actually not optimal. So it doesn't run to all the different combinations. So interestingly, on this very, very simple example, these classical solvers can already fail or provide a suboptimal solution. And for this, there was the introduction of the maximum independent set solver, so the maximum independent set package that we developed with Pascal. So this is an open source Python library that tackles this particular combinatorial optimization problems. And as you will see, it works both on classical and quantum systems, especially neutral atoms type quantum systems, due to its backbone running on Pulsar. So any kind of neutral atom system can execute the code itself. And it provides a very, very high level interaction for solving this problem. So indeed, for the first exercise, in the comment, I almost left the actual solution to it. You just need to define an instance which is generated from a network X graph. So you define your graph as a network X object, and then you create this MIS instance object. This MIS instance object will be the graph structure with some intelligent and automated labeling associated to it. You can also draw it out. You have a similar representation of what we have seen with the network X package as well. And then if you want to solve this problem, it is actually very, very simple. You just need to configure a solver. So this can be done in the following two lines, just to define a backend. If it's left empty, it will use a classical solver. If it's specified what backend, what resources it is able to use, it can work in on emulated or even quantum hardware executed fashion as well. And you can also limit and control the number of solutions it would provide to you. Once you are done with the configuration, you just feed it to the MIS solver object, both the instance you defined, so the MIS instance, and the configurations you have defined, and run the solve command, and it will list all the potential MIS solutions. In this case, it highlights the two MIS solutions of this problem. Again, in this provided initial code, there was no actual backend defined, so it did classical or optimized heuristic approximation to this. However, if you define a backend, such as, let's say, I defined as a backend the QTIP backend, so a quantum emulator, it will shift to a quantum-based execution and resolve the same instance to this. So what is interesting is that the entry point here was just the graph definition. I did not define how I want my atomic register to be encoded. I did not define how I set up my pulses. All of this is automated and is done by the solver itself. So this is what I meant by a very, very high level interaction. To use this MIS solver, you just need to define a graph and you have less than 10 lines of code to solve the MIS solution, even involving quantum systems. So this is the current state of maturity, that you are able to have access to these libraries that automate everything for you. Will it always be the best solution? Probably not. In actuality, you might want to start going a little bit deeper to try to optimize it, depending on the type of graph, the type of instance you are dealing with. But as you have seen with the first exercise with Pulsar, that this might be a very, very low-level interaction that requires a lot of specific knowledge. So it might be a bit too deep in the programming. So what you would try looking for is something of an in-between. And Vincent has foreshadowed that part, that with Pascal, we are currently working on Python library called Toolkit that will create this internal link, providing you with a programming language and a programming library that is more abstractified and higher level than Pulsar. So you have a lot of automations in place, but still allows you to finally control certain interactions in order to optimize it for any kind of current and next generation implementations. And since we have run out of time, I apologize for that. I'm not sure if there are any more questions left in the chat still.
Yes, there was one to which I'm not sure if I have an answer. Would you have a tutorial to solve the traveling salesman problem? I don't think we have, but I wanted to check with you.
Currently, we do not have a tutorial on that. However, we are working on a tutorial for the capacitated vehicle loading or vehicle scheduling problem, which is a first step towards a traveling salesman type implementation.
And this was the only question that I didn't answer or you didn't answer in the chat.
Perfect. So with that, we have reached the end of this quite an extensive and quite long session. So on our side, from PASQAL side, we thank you very much for your attendance and for being here. and hopefully these materials and all the topics we discussed are useful for your continued exploration of the quantum systems. We are very happy for all this attendance and all this usage. And of course, we are at your disposal. Even later on, if you have any further questions, feel free to reach out to us.
Thank you very much to all of you, and I think we can call it today, Christian.
From our side, yes. I'm not sure if the others would like to say something as closing words.
Thank you very much, Vincent and Christian, for that. It was the first step, so we are very fond of any remarks on how this seminar have been received by you. So don't hesitate to make comments to Christian, Vincent, and us. Thank you very much.
Thank you, everyone. We'll see you next session.
Thank you, everyone. Bye-bye.
Thank you, everyone. Goodbye.